It's always in the nature of mankind to search for data and information at the same time. So many times you be on YouTube, Google, internet, so many kinds of internet, and you're downloading the videos, you're downloading audio files, you're downloading these pictures. But remember, these pictures you download need to be stored somewhere. But unfortunately, sometimes the space where we store them is never enough. Of course, there are different formats in which we store these images, we store these videos, depending on what storage device that you're using. But it's never enough. Now, we're asking ourselves, where did this all come from? We are going to discover the evolution of storage technology, the different innovators trying to come up with different ways they can form different storage devices to ensure that there is enough space created for the information accumulated from the different human beings. Because you want to look at the information, you never want to delete that information at the end of the day. At least you want to store it. Maybe sometime in the future you may need to refer to that information. You may need to refer to that video. Welcome to this episode of SMART-TEC. I'm Andrew Barije, and today we are looking at the evolution of storage technology, getting to understand where we came from to where we are lately, and that's the cloud storage. That and more coming up. There are many factors driving data storage evolution. The first is digital creation. Whether it's media, industrial 4.0, IoT, or the digital infrastructure of companies, these are catalysts generating huge amounts of data worldwide. Consider how we use machines to work and play in our households. Pre-pandemic, majority of the workforce were in offices with all the connecting devices in one place. But now, as we are working from homes, coffee shops, and co-working spaces, the video conferencing technologies and social media we use are generating more and more data. As a result, so much data is being captured from the edge, both static and moving. Coming to Industry 4.0, every company is adapting and making their machines smarter. IoT is not just one of the workplace anymore, but has become part of everyday life. For instance, home automation generates a huge amount of data. Think about the Alexa and Google Home devices being used across the world. Everything from home appliances to our kids' video games is generating data. In the past 2 decades, due to exponential rise of data usage, data centers developed stringent requirements for greater storage capacity per square area and faster data transmission. The industry continued to evolve. Innovators focused on finding ways to achieve larger capacity and faster throughput while using limited space and staying within their power budget. Flash technology became very popular for its small size and ability to deliver faster insights using significantly lower power consumption than hard drive technology. However, even though this option solves some size of power problems, it has limitations. For example, the lifespan of most flash devices allows you to write data to them only a certain number of times before they fail mechanically. Over the past 90 years, data storage evolved from magnetic drums and tapes to hard disks, then to mixed media, flash, and finally cloud storage. That's where we are today. And as our storage needs increase, innovation continues to evolve in multiple areas. Let's take a look at the paradigm shift to data storage at edge. Big data plays a pivotal role in almost everything we do these days. But it's no longer enough to just have access to data-driven insights, particularly if they are outdated and obsolete. As the amount of data generated grows and data capture increasingly moves closer to edge environments, urgent processing is critical to deliver timely intelligence that reflects real-time circumstances. Organizations are progressively experiencing more pressure to obtain and apply insights rapidly before situations change. This fact makes it imperative for business leaders across all mainstream industries to embrace active data and deploy ways of capturing and transporting it for immediate processing. Let's take a look at the challenges of managing big data. To optimize artificial intelligence for the future, we also need high-performance systems. These could be storage or cloud-based systems processed by modern data-hungry applications. The more data you feed these applications, the faster they can run their algorithm and deliver insights. Whether these are for micro-strategy tools or business intelligence tools, this is usually called data mining, and in the past, we did it by putting the data into a warehouse and then running applications to process it. However, these methods are rife with challenges. Data-generating devices are now continuously churning out ever-growing amounts of information. Whether the source is autonomous vehicles or healthcare, and whether the platform is a drone or edge device, everything is capable of generating large amounts of data than before. Until now, the data management industry has not been able to capture these quantities either through networks, 5G, cloud, or any other storage method. These circumstances have led to 90% of data gathered being dropped because of inadequate storage capacity and the inability to process it quickly and deliver it to a data center. The outcomes also apply to critical data captured at remote sites that have no connectivity or cloud applications running at the edge. It's essential for us to develop ways to resolve these challenges. Solutions that may include timely capture, transportation to data centers, cloud and immediate processing using a single lightweight storage that enable us to enjoy the advantages of putting artificial intelligence to work for humanity. What could the future be like in brief? CIOs are always looking out for new ways to operate infrastructure cost effectively. To prepare your company to get high-performance results in the future, all applications you are running need to be highly responsive. Not all data is accessed all the time. Some data sets are only accessed for a short period of time, and then they fade out to date. To optimize your infrastructure in terms of cost, performance, and space elements, you should analyze the data characteristics and identify datasets and segments that aren't needed constantly. Then, design a data architecture that includes slow-speed storage for a non-critical data. This could be a hybrid of fast storage technologies and hard drive technologies. Layer the architecture so that the only active data requires fast storage and the rest can be stored in lower locations. There are certainly different types of products coming up in flash SSD drives. Higher-end storage systems will also follow this technology. The data space is seeing some breakthrough innovations to address storage migration and deployment challenges, and one needs to stay abreast to benefit from the data available to us. Briefly, let's review the modern storage technologies that you need to know. Fast data volume growth and people's habit of consuming increasingly more online content encourage storage producers to continually innovate. What are some of the new technologies and what are their characteristics? Let's take a closer look. Why the need for innovative technologies? First, a few numbers to put to the discussion in context. Worldwide, 4.3 million videos are being watched on YouTube. 400 hours of new videos are added, more than 474,000 tweets shared, and there are over 3.5 billion searches on Google every minute. In 2018, study IDC reported that there were around 33 zettabytes of data in the world. They estimate that by 2025, this number will grow to 175 zettabytes of data. That's so much data that it would take around 1.8 billion years of a single user to download all of it using current internet speeds. 4.333 billion people are internet users at that moment, an increase of 8% from 2018. Out of them, 3.534 billion are social media users, up 9% from last year. More than 3.463 billion people use social media on their phones, an increase of 7.8% from 2018. It's no wonder that the need for faster data access and high data throughput storage solutions is bigger than ever and growing. That's why there is a rapid adoption of new technologies that complement modern storage approaches. Some of these new technologies, one of these storage class memory or non-volatile random access memory, can retain data even after the electrical power is removed. Since each byte has its memory address, NVRAM is very fast, especially in comparison with dynamic RAM, which has page level access, or with standard and has block level access. There are several types of NVRAM technologies. The oldest one, static RAM, has more complicated structure than the DRAM, with at least 6 switches and more active connections. The switches are configured in such a way that the clip will retain its state without fresh, making the SRAM very suitable for reads and low latency applications. However, this makes it harder to write and more prone to degradation over time. Newer non-volatile memory technologies such as ferroelectric RAM and MRAM have better specs and use causes than SRAM. FRAM uses ferroelectric capacitor architecture as a storage element. There is an electric dipole that moves the switches and polarities with an external electric field. Temperature and free electrical charges cause the dipole to loosen up over time and cause failures eventually. Compared to FRAM, MRAM does not require any type of motion because it is based on ferromagnetic material magnetic state at a point in time. It also does not wear out in time and it is not affected by temperature. MRAM also has faster access and cycle times. Other technologies are on the way like phase range RAM, Sonos, resistive or nano RAM. Only time will tell which ones are reliable and cheap enough to mass produce and hit the shelves. NVRAM also comes in the form of NVDIMMs, although some NVDIMM technologies such as NVDIMMN do not have a persistent RAM technology on board. It only combines DRAM and NAND chips on the same board and copies data from DRAM chips to the flash in case of electrical power loss. On the other hand, NVDIMMP will use some persistent memory technology described above and complex controller and buffer scheme. Release time will probably be somewhere in the coming years, likely along with DDR5 timeframe. Use cases can benefit from the advantages of persistent memory or applications that use fast transaction logging and in-memory computing like databases. Fast technology development and affordability might come a reality due to market leaders such as Intel and Everspin, who are currently focusing on this technology. For now, the price is quite steep. Intel is selling the 128GB NVDIMM module at around $570, the 256GB at $2,100, while the 512GB can be acquired at the outstanding sum of $6,700. Hopefully, the prices will drop along with technology adoption. Another new technology is NVMe over Fabrics or NVMe-OF. This protocol allows transferring NVMe storage commands between servers over InfiniBand and Ethernet using RDMA technology. The RDMA protocol enables different applications to transfer memory information directly bypassing the operating system and CPU, having very low latency and saving computing resources. With NVMe-OF, this can be done over Ethernet cables by connecting the nodes in high-performance computing or distributed storage scenarios. NVMe protocol can be transported over various media like FC, InfiniBand, Ethernet, or next-generation fabrics. The most popular NVMe over Ethernet implementations are ROCEV2 and IWARP. Although the IWARP may sound like an upgraded warp drive from Star Trek, it is not that fast compared to its cousin, ROC-EV2. Due to its complexity and added overhead, ROC-EV2 is lighter, faster, but lacks the robustness of IWARP. Given that IWARP uses TCP, while ROC-EV2 uses UDP frames. Both are routable protocols, thus the case scenario can extend more. Even though the cost of a slightly higher latency and unreliability when using UDP to make ROC-EV2 fully reliable. However, reliability checks can be added inside the RDMA protocol stack in the future. Although both ROC-EV2 and IWARP protocols need a physical adapter installed on each host in the network, IWARP can also be tested with regular Ethernet NICs using soft IWARP. You can clone it from GitHub and try it yourself. Well, what is the impact of these new technologies? Both SCM and NVMe OF technologies helped pave the way for some exciting new approaches in storage. One of these is computational storage. We take the old storage system idea and turns it the other way around. Instead of moving the data to the processing node, the computation is done much closer where data is restored, thus saving significant host CPU resources and time. Although a storage fabric comprised of fast media and NVMe is blazing fast, computational storage systems kick things up to notch. CSS relies on SITU processing of data by adding ARM processor into the controller of an NVMe SSD. Data still needs to travel over the CPU, but this happens much faster due to the Common Flash interface. Common Flash interface is a standard introduced by JEDEC to allow storage of data sheet params located in the device. This information is stored in the form of CFI cables, which can be queried by the application that requests data. For example, NGD systems use an ARM Cortex A53 processor embedded into a controller of an SSD disk. Samsung uses Xilinx FPGA with ARM cores to offload the CPU with tasks like compression, deduplication, encryption, or even analytics. AIDETCOM developed an NO-load accelerator. One of those fit into a 2.5 in U.2 NVMe SSD form factor, but instead of flash chips, task Xilinx FPGA accelerator and some memory. This approach takes advantage of keeping the current disk setup and using the PCIe bus to offload jobs like erasure coding, RAID data, data compression, deduplication, and so many more. A second approach is intent-based storage, a new interesting storage solution with great potential. Argumenting the idea behind computational storage, companies like Datera and Hammerspace have developed some of the great proprietary solutions. Hammerspace converges multi-cloud environments under the same hood, using a global file system on top of the actual data. Each piece of data receives its own metadata that tells the global file system where the information is, how to access it, and details about it through a metadata engine. Once the metadata index is created, a machine learning algorithm comes into play, analyzing metadata through analytics and offering more details about data while also continually improving file access and performance. Datera is another crucial player in the software-based services industry. They offer a solution similar to that of Hammerspace, but they also provide a way to interact with storage environment via GIU or API, according to customer needs. Depending on customer resource requirements, a complex QoS implementation of the storage infrastructure can add or remove compute nodes automatically, move data to hotter or colder storage tiers, making on-the-fly scalability possible.
It's really amazing from where we've come from regarding the storage, from the cassette tapes, coming to the CDs, flash disks, chips, and of course the ultimate being the cloud storage. And of course, at this time, we are going to get into a short commercial break, and definitely I'll be returning with more. But this time around, when I return from the break, we are going to be looking at the cloud storage. Talking about the cloud storage, as we speak today, it's the optimum, let me say that, it's the peak of storage where we can store our records in space. I understand they could be very complicated terms as you're watching, but I would urge you to watch this show over and over again. You will be able to grasp whatever matters that we are discussing today on SMART-TEC. Let's get into a short commercial break. I'll be returning with more.